Let us solve one more numerical on your impact loading. The numerical says that we have to determine the maximum height from which a weight of 25 Newton as shown in this figure. This is the weight of 25 Newton and some height is there. Let us say this is height h. This is height h. Right. So we have to determine the maximum height from which a weight of 25 Newton as shown in this figure can be dropped onto a flange attached to a 10 mm dia rod. This rod is of having diameter 10 mm and this is your flange. 10 mm diameter rod of length 1 meter. The rod length is 1 meter. If the maximum stress is not to exceed 150 megapascal. The maximum stress in the flange or in the rod is not to exceed 150 megapascal and the Young's modulus of elasticity is 200 gigapascal. Right. The Young's modulus of elasticity for this rod material is 200 gigapascal. We have to solve for the maximum height so that the stress cannot exceed 150 megapascal. So that means the maximum stress that is induced in the bar should not be greater than 150 megapascal. Right? It should not be greater than 150 megapascal. We know this is when this weight is dropped from some height h, when it strikes the flange, it exerts a impact loading on the flange and the bar. Right, it impacts a impact loading. So because we know from our discussion on impact loading that the stress developed in the impact loading is more than the stress developed under the same load if it is applied under static condition. Right. If same load is applied on impact loading and static loading, then the stress developed under impact loading is more than the stress developed under static loading. So we can say in this case the stress which is developed under impact loading, because it is more, so the impact loading stress should be less than or equal to 150 megapascal. It should be less than or equal to 150 megapascal. It cannot exceed 150 megapascal. Right. And we know that the impact stress will be equal to your static stress into impact factor. Static stress is if this load 25 Newton is applied on this flange, if under static condition, then static stress will be load per unit area of this rod, right, into impact factor is 1 plus under root 1 plus 2h upon delta static. If you put the formula, if you put the values in it, what is the load? This is 25 Newton. What is the area of the rod is? This is a circular rod, diameter is 10 mm. So the area is pi by 4 d square, where diameter is 10. We are taking this is in Newton. Just make one thing very clear, in the strength of material, it will help in your further discussions also. This is in Newton and I am taking this is in mm, right? So the unit of this area will be mm square. So the unit of stress will be Newton per mm square. So in strength of material we are not converting this mm into meter. Just in every numericals we are taking the values of the length or dimensions in mm only, because one thing, this Newton per mm square, that is 1 Newton per mm square is equal to 1 megapascal. This will be equal to 1 megapascal. Every stress or every unit in the strength of material is given to you, any data is given to you, that is the maximum stress value, Young's modulus of elasticity, modulus of rigidity, all these values are given in megapascal or gigapascal. Right. So if you say that 1 gigapascal will be equal to 10 raised to power 3 megapascal. This we know, right? 1 gigapascal will be equal to 10 raised to power 3 megapascal. So we are taking the dimensions in strength of material as Newton per mm square, and 1 Newton per mm square is 1 megapascal. You have to remember this. No need to convert every unit in Newton per meter square, right? If you say that Newton per meter square is 1 Pascal, so we are not converting every unit in pascals, rather than we are converting every unit in megapascal. So keep your dimensions in mm only, so that the calculations would be easy. No need to take the 10 raised to power 6, 10 raised to power 9. Just make the calculation easy. We are taking Newton per mm square, right? That is equal to 1 megapascal. So I am taking all the dimensions in mm only and all the loads in Newton, right? If in any question the loads are given in kilonewton or mega Newton, just convert it into Newton and all the dimensions in mm, so that the results would be your megapascal, right? So this is 25 upon area is pi by 4 d square into 1 plus under root 1 plus, this is 1 plus 2h upon delta static. Delta static, as we know that the delta static will be, in case of normal load, the delta static will be load into length upon area into Young's modulus of elasticity. This we see earlier, right? So this is 2h upon delta static, that is WL upon AE. If I put the values here, this is 25 upon pi by 4 d square into 1 plus, this is plus 1, right? 2h upon weight is 25. Now this length is in meter, right? If I am taking every unit in mm, so I convert this length into mm. This is 1000 mm divided by area is pi by 4 d square, this is mm, and E, the value of E is given in gigapascal, so convert it into megapascal. So multiply by 10 raised to power 3 plus 1. It is should be less than or equal to 150. It should be less than or equal to 150. If you solve this equation for this height h, then you will get the height h should be less than or equal to 175.96 mm. That means the maximum height which you can afford in this case will be 175.96 mm, right? This is the maximum height you can afford in this case, right? So this is the maximum height I can afford. So if the height is less than 175.96 mm, then the stress or the impact stress induced in this bar or in this flange should be less than 150 megapascal. And at a height of 175.96 mm, the maximum stress induced will be 150 megapascal. We have, if you increase the height, that is, if you in the question, let us say if in the question you round it off to 176 mm, then your answer will be wrong, right? If I exceed the height, then the stress value will be exceeding 150 megapascal, so the answer would be your 175.96. It should not be 176, right? Because if height increases, your 150 megapascal will increase. So the answer will be 175.96 mm. This should be the maximum height we can afford to, so that the stress induced in this flange should not be more than 150 megapascal. This is how you can solve the numericals on your impact factor or impact loading.